Now, let's take a look at this equation. Okay? This is again describing the sound pressure field in a tube like this. If you look at this, I say, okay, what I want to do is find out at what value of D, meaning away from this expression will be minimum. Where can it be minimum? I want to find the pressure minima. Right? Because waves go and come back and they have some interference effect. And how would you find that? Exactly. Maximum value this can take is 1. Okay? And what values will that will give it 1? They should be integer multiples of its argument, actually m pi. Okay, so from here we can easily write and the value and the minima, this is where they are, but the value of the pressure let me just write this clearly here, just a little bit better. Okay. How would we find the maximum? Pressure maxima would be, of course, when you make this equal to 0, and that would be at the odd integers of odd integer multiples of pi over 2, and we can describe it as actually, let's see now. and maxima take place at something's not right here. Now let's, excuse me, let's take a quick look at this. If there are no losses, okay, and alpha, beta, gamma are all zero, what happens? Then P minimum is zero. Just like the perfect wave, when there are no losses, it goes and the minimum in a tube, let's say, okay, sound pressure is zero. In this case, however, okay, I will use a little red pen. In this case, sound pressure does not really reach a zero value. There is always an amplitude at the minimum because of the losses. Okay, that's the big difference here. And this complex mathematics approach actually is very helpful in terms of finding out the relationships for minima and maxima. But now I'm going to write a little prescription as to how you measure them. Okay? So let's see. Okay. So to measure okay, one, determine the spacing. Between determination and the nearest minima, nearest minimum. And nearest minimum, of course, is okay for the spacing gives us half of a wavelength, and from here then the value of gamma is determined. This is number 2. It's determined by measuring pressure at 2 successive minima. For example, at n and n plus 1. And if we do that, let's see. If we do that and take the difference, the difference will give us a relationship between the ratio this is absolute values, the difference in the absolute values. And then divided for the max value. Once you write it, let me explain what that's all about. Okay. What we're doing is we're taking a microphone, okay, we're moving it, we find a minimum value, and we keep on moving, we find the second minimum, the first minimum and the second minimum. And in between, there's a maximum value. So we have these 3 values, okay? 2 minima and the maxima. Mathematically, based on what we have derived, their ratio, the difference to the maximum value is very simple. And what is that? Wavelength and the losses in the system, gamma, across the pipe. As simple as that. And you can see why that becomes very important. If the loss is so small, by the way, here's something that you should keep in mind. In acoustics, we talk about large, small, far field, near field, low frequency, high frequency. They're all relative. They're all relative with respect to some wavelength, some frequency perhaps. In this case, when we say very small, we're talking about with respect to the wavelength, meaning with respect to a frequency. So a value of loss may be considered to be very small at one frequency, but not so at a higher at a different frequency. Okay, so if this value, if the smallness is satisfied, then you can say that, in fact, this ratio is roughly equal to this. But if this is not satisfied, then you use this original relationship. And once again, what you're doing is you're taking a microphone, and in fact, these measurements are usually done with a very thin pipette, in front of which is a tiny little microphone, so that that little pipe does not disturb the acoustic field. And you start moving it, okay? You start pulling it out, and either you look at the sound level meter, or you look at the oscilloscope to see what amplitude change there is, and establish minima, two minima, and the maximum between them. And that gives you that particular result. Now, you can see this is the difference divided by. What happens if you add these instead of subtracting them? Then the mathematical relationships that we have derived will give you a different, will give you a different expression, and therefore a different capability for a different result. And that is cosine gamma lambda over 4 tangent hyperbolic pi you can see that from that different ratio, you can obtain alpha L numerically. Let's recap what we did. Okay. In the last 1 hour, what we did was write the wave equation in a different form. Okay. Usually we write it as e to the ikx minus or plus e to the ikx cosine, but now we wrote it in terms of hyperbolic functions. Okay. That after maybe a complicated derivation, it gave us at the end relationships that actually allows us to make measurements to understand or to determine what the material properties are, what losses are in a waveguide. As simple as that. That's all we did. And I'll get you some homework problems that will help you review these and develop them further. Do you have any questions about these? Lots of mathematics for good measurement results. No? None? Okay. What we'll do now is move along to something related, but not exactly the same. What happens if the duct walls are flexible? Okay? Flexible walls. Okay. The dotted lines suggest the flexibility of the surface. Of course, they can also flex to the inside, so it just vibrates back and forth. Ability to vibrate back and forth. Okay. Now, again, remember that all the equations are linearized equations. Are linearized. Now, as we know from before, pressure gradient produces what? Acceleration of the fluid, right? So we have, this is something that we use for boundary conditions also. A change in pressure produces that. And the velocity gradient, on the other hand, produces compression or rarefaction, okay, protractions. And these you have from a few weeks ago when we developed these wave equations. Okay, now, when the duct walls are flexible, the continuity equations must be satisfied, okay? So we have to modify the continuity equation because the area is no longer constant, cross-sectional area. Okay, so the rate of influx of, let's say, gas in this case, into a unit length of duct causes a change in density and pressure. Remember, for rigid walls, continuity equation, but and S is the cross section. And velocity is S times particle velocity. So for flexible walls, we must now include the wall stiffness. Okay, and wall stiffness we can say is pressure divided by change of cross-sectional area. Pressure divided by change of cross-sectional area. Pressure is not static, right? Pressure is not static. And what that means is as the pressure excites this, okay, as a result, wall oscillates, and as a result, inertia comes into effect. So suddenly you have another source that's influencing the system. So the wall impedance comes into effect, which we have inertia and stiffness. So instead of just the wall stiffness, we include now the complete impedance of the system to make it complete. Now the flow gradient has a new expression. This is kappa, by the way. Please add a negative here. It's the yep. Okay. Let's just look at it for a quick second. When the walls are rigid, as before, the relationship with the flow gradient and pressure fluctuation with respect to time is very simple, given by a constant cross-sectional area. But now cross-sectional area is not constant, okay? So it has some sort of stiffness. If that's the case, that stiffness, or this is the admittance, inverse of the stiffness, you add it to the compressibility. But now we're saying that it isn't just the compressibility effect, you have a wall that's moving. It's not a membrane. If it were a membrane, its inertia may not be important. But now it has its own inertia. And then instead of Kw, we now utilize the full impedance of the walls. Walls have stiffness. If you push it, it comes back. Okay, it also has a certain amount of mass. If you substitute the full impedance instead of just the stiffness and make appropriate substitutions, omega 0 here is stiffness of the wall divided by its mass per unit length. So it gives a resonance value, okay? At a certain frequency it resonates. And so this is the wall resonance. We go back, we take kappa or rho c square, 1 over rho c square out, and then we repackage it, if you will. And you have a little expression here that adds to the resonant frequency, okay? If you look at this, expression now, that actually is an added resonant frequency due to the stiffening of the air, okay? Because it's like a balloon, okay? The membrane is not very stiff when you don't have air in it. But the higher the pressure in it is, the stiffness is somewhat different. So this is just a little bit addition to it that changes its stiffness. And it gives it a different frequency. You can see the relationship now. And in fact, the gradient now can be 0 if these two are the frequency of the sound that's coming in is equal to this new frequency, or it could be very large at a very close value. So we can let's see. Originally we had yes. What we have that's different, this is the difference compared to the rigid-walled tube. Okay, this particular one is the difference, and we can now say that the wave velocity in the duct is modified for very long wavelengths. In other words, this is very, actually, it reminds me of an application. What it does is the wall motion changes the speed of, effective speed of sound in the pipe. So I'll give you a very excellent example of this. And there are patents on this. When you have a pipe, for example, hydraulics. Okay, you have a hydraulic pump, that swash plate goes very loud, pop, 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 pop noise from a diesel engine or from any kind of pump, really. It could be on airplanes, ships, or factories, etc. So you have these very strong pressure pulses generating huge amount of vibration and noise that transmit through the pipe. And one thing that can be done, and that is being done, is you put around it a sleeve with, say, a liquid, okay? Now, different air pressure. So as the pressure comes through here, of course it's vibrating the walls, but as soon as it comes in here, the speed of sound is now different, okay? So you have one speed of sound here, another speed of sound on the sleeves, okay? And when they come over here, they have a canceling effect, and it does not propagate the sound. And you can see here also elements of that. Speed of sound is modified because you now have a flexible surface, okay? So you have to think about these, and they have very, very good applications later on. So just the flexibility changes the effective speed of sound. And see, if this were 1, this is the original, I think, yes, it would be this, okay? If this were equal to 1, that would be this relationship. And kappa, as you know, is 1 over rho c square, okay? And then we fold it into that c square and say that effectively it is changing the speed of sound. And in fact, you can measure that taking place. So let me just conclude this by a few comments at the end. Okay, let's just summarize. As omega increases from 0 to the resonant frequency, C phi goes to 0. In other words, when omega, yes, when the frequency becomes equal to omega 0, okay? What happens then? Where does the energy go? Okay, wave energy is used entirely to excite the lateral wall vibrations. Okay? As simple as that. Now suddenly you see that you have a flexible pipe. You adjust its flexibility so that it just prevents sound from transferring, but at only one frequency, not at all frequencies. So if you have let's say, a pump that's sending pulsations at a primary frequency with a lot of other frequencies, you can get rid of the primary frequency if you are able to adjust the wall flexibilities. Okay. Secondly, for frequencies between the empty wall resonance, okay, and also the air stiffened wall resonance, then what do we have? C phi is imaginary. Now the modified speed of sound becomes imaginary, Acoustic motion is evanescent, strongly attenuated. That means no true wave motion can exist. And lastly, if omega is larger than omega 1, of course, now we have supersonic speeds at higher frequencies. And as omega goes to very, very high frequencies, it reaches the speed of sound. All right. Any questions? You look tired. Are you tired? What have we learned today? Give me a quick summary. What do you think you learned today?
I think we learned about modes.
Modes? Mm-hmm.
We learned about flexible walls.
Flexible walls, okay.
Wave equation or the quantitative equations change.
Yes, mm-hmm, exactly.
We learned about complex wave number.
Yes, complex wave number and expressing the pressure field or the acoustic field in complex terms. A couple of lectures ago, we talked about wave equation, how we derived wave equation. And then we came back and we used part of that now. Because always in these derivations, there are assumptions. And so you cannot apply them to all conditions. This is true for all aspects of engineering, okay? You need to know the assumptions behind the derivations of certain equations. In this case, because the wall is flexible, we went back and we modified. Actually, I did this as a shortcut, but we could have gone to the original equations of continuity of mass and so on, and then derive this, but it would have come to exactly the same result. Here we did a physical approach, saying that we need to take into account both the stiffness as well as the inertia for a complete impedance. We did not include any damping in this because it would have minimal effect actually, but you can just include it in here. So, and that gave us the notion, I'm going back now, but that gave us the notion that the flexibility takes some of the energy away. And as a result, the speed of sound is now modified. And in fact, you can modify the speed of sound to play with how much sound will be transmitted and so on. Earlier, we spent a lot of time on deriving complex equations and with the express purpose of how we would be able to use very simple expressions at the end for measuring properties of materials. The process was complicated. It's like preparing a very complicated dinner, but at the end, it's very simple to eat, okay? All right. I'll see you next week, unless you have any questions. Any questions? Okay, thanks.